So in the last episode, we looked at the concepts of charge and static electricity. And now in this episode, we are going to continue looking at the electric circuits topic, and we're going to look at the concepts of voltage and current. Let's get into it. So let's start by talking about voltage, or what we often refer to as potential difference. So we tend to use these two words, potential difference and voltage, interchangeably. As usual, here in the green is the what the SACE board stipulates you need to know. It's very much our learning intention and our success criteria that we need to have. So I think it's worth going back a few steps before we talk about voltage and talking about hopefully what you learned about work and the concept of energy in either year 10 or maybe in your earlier years of school. So when an applied force causes an object to move, work is done. So when we push on something and it moves, or when we lift something, so we're pulling a force against gravity and it moves, work is done. The amount of work done, which we give the symbol W in physics, is equal to the product of the force applied, F, and the displacement or the distance travelled of the object. So work equals force times displacement, or you can think of this as distance. Energy is defined as the capacity to do work. So this is what work is. Energy is just the capacity to do work. So if I want to do work, I need to eat some food to get some energy to do work. Energy is the capacity to do work. The energy gained by an object is equal to the work done on it, or the energy lost by an object is equal to the work it does. So basically, the change in energy is equal to the work done. If I do work, I lose the same amount of energy. If work is done on me, i.e. I'm pushed up a hill, I will gain gravitational potential energy equal to the work done. Any charge placed in an electric field has electric potential energy, just like any mass placed in a gravitational field has gravitational potential energy. So it might be a little bit confusing, a little bit above what you've done in previous years, but if we hold any object up above the ground, it's in a gravitational field, it's above the ground and the Earth's gravity is pulling it down. When we let it go, it will gain speed, it will gain kinetic energy, and it will have the ability to do work. That potential energy, that stored energy it has when you're holding it off the ground, is its gravitational potential energy. Electric potential energy is basically very similar, but instead of applying to masses where there is gravity present due to a large mass like the Earth, it applies to electric fields like those that we produced by basically charging up objects and having this electrical current want to jump from one object to another. And we'll look at that more with a Van de Graaff generator later on as well. So mathematically, voltage, which we give the symbol delta V, is defined as the work done per unit charge in moving between 2 points. That's in an electric circuit. So voltage equals the work done divided by the charge. Voltage is, I think I said this before, measured in volts. Work done is the same as energy. It's measured in joules. And Q, which we learnt about in the last episode, is charge measured in coulombs. That should be a lowercase q, although we do tend to use both lowercase q and uppercase q for work. Now, we'll do some problems on this mathematically, but at the moment, mathematically, that might not make sense. So let's think about voltage in a little bit simpler, less mathematical sense. Voltage indicates the energy of the charge that is flowing. That's in an electrical circuit. High voltage indicates high energy and low voltage indicates low energy. So the charge that's coming out of a 240 volt power socket in your house is going to have a lot more energy than the charge that comes off a typical 1.5 battery that you put a 1.5 volt battery that you'd put in a remote control, or a 5 volt battery, which is what most USB devices like your mobile phone are. Voltage is given the symbol delta V, as I've already said, and is measured in units of volts. Don't let all the V's confuse you. It's very rare that we have voltages measured in volts. We don't have length isn't measured in lengths. And length, we give the word D, but we give meters M for the unit. Time, we give the symbol T, but it's measured in seconds, which is S. Here, voltage, delta V, volts, V, we use V everywhere. So it can be a bit confusing, just be a little bit aware of that. But volts are the unit, voltage is the amount of, is the quantity, as in voltage is like the time, volts is like the seconds, time being the quantity, seconds being the unit. So yeah, voltage, it's really about the amount of energy. I think in the class I talked about the waterfall example. If you compare an electric circuit to a waterfall, a high voltage would be like water that's flowing over a really high waterfall, so it's going to have lots of energy when it hits the bottom of the waterfall. A low voltage would be just coming over a very shallow or not very deep waterfall, and the water is not going to have built up that much speed when it reaches the bottom. Okay, there's a couple more things about voltage that we need to talk about that relate to what's here, and we'll do that in the next slide. So when we want to measure voltage, we use an instrument called a voltmeter. So a voltmeter here, and we'll do this when we have a prac, and we'll use these. And voltage is always measured in parallel, and we're going to talk more about parallel and series circuits later, but I'll briefly show you what that means in a sec. But basically, because we're interested in that potential difference between 2 points, we're interested in basically measuring something across 2 points in the circuit. That's how I remember it. So if we were going to measure voltage here on this diagram here, let me just get rid of that, we would put a voltmeter and we would measure it on the voltage drop we could measure across that light bulb. Or alternatively, and you can see that's almost the same, we could measure the voltage drop here, or the voltage being provided across this power supply. Now you can see between there and there and there and there, there's no other things in the circuit that will use energy and cause the voltage, cause things to lose energy or the voltage to drop. So it's really the equivalent in both cases. And basically, when we draw electrical circuits, V indicates that we have a voltmeter. And as I said, we'll spend a little bit of time on electrical circuits later on, but basically that's what we mean by measuring in parallel. We have it, if you like, parallel to the light bulb or parallel to where the thing is, which basically means across 2 points. Another thing I just want to introduce, because this comes up a lot in this sort of topic, is the electron volt. It's a unit that we use a lot in physics, and it's a bit confusing because an electron volt isn't really a volt. An electron volt is actually a measure of energy. So an electron volt is the change in potential of an electron when it moves across a potential difference of 1 volt. It is a measure of energy. So basically 1 electron volt is equal to 1.6 times 10 to the minus 19 joules. So if you've got 2 electron volts, that's 2 times that. Or if you've got 10 electron volts, it's 10 times that. So in a sense, if you want to go from, oops, that's not a pen. If you want to go from electron volts into joules, you times by 1.6 times 10 to the minus 19 joules. And if you want to go from joules to electron volts, you divide by 1.6 times 10 to the minus 19. And sorry, I said joules, but I shouldn't have. Well, the units would be joules before. Well, and that will give you, yeah, your answer in electron volts, because I've got the units there. Don't know if that made it more confusing by doing the units, but just remember, electron volts to joules times by 1.6 times 10 to the minus 19, joules to electron volts, divide by 1.6 times 10 to the minus 19. And if you're wondering where that sort of comes from, if you think about that formula we had before, which says basically delta V equals work done divide per charge, or work done over charge, if we want to know the work done in, well, if we want to know work done, that's our unknown, and we apply that charge across 1 volt, and if we put 1 electron across 1 volt, the charge on an electron is 1.6 times 10 to the minus 19 joules. Then we put that all into, rearrange that formula, we get work done equals delta V times Q, which is equal to 1 times 1.6 times 10 to the minus 19. So that is equal to 1.6 times 10 to the minus 19 joules. So that's sort of a mathematical explanation of where that 1.6 times 10 to the minus 19 comes for the conversion between electron volts and joules. When we're dealing with a small number, well, just individual charged particles like electrons and protons and how much energy they have, we often use electron volts. We also did use electron volts to describe how much energy the particles from radioactive decay had in our last topic, and typically there we talked about mega electron volts, so millions of electron volts, because the particles of radioactive decay are moving really fast. They're very energetic, dangerous particles, if you like, that can damage living matter, and they have lots of energy. So that's where you might have also seen that term electron volts and how that relates to voltage and charged particles like electrons. I hope that's clear. Okay, that's it for voltage. Let's move on to current. So hopefully current is a little bit simpler to conceive than voltage. Electrical current is the rate of flow of charge, and that charge is in most circuits is electrons. So I, which is current, and it's measured in amps, A, is equal to Q, which is the charge. I haven't defined that, but we've already talked about charge being Q, T being time. So if we have a large amount of charge, we'll have a large current, a small amount of charge, a small current. If we have the current moving really quickly, so the time is very small. If you're moving quickly, you're not moving for very long, so time is small, then you'll have a high current. If the time is large, the current's moving very slowly, slowly, so the time it takes to move is very large, then the current would be small. Current is measured with an ammeter, and current is measured in series within the circuit. So I probably should have pre-drawn that diagram, but if I think of like that simple circuit that we had before, we use the 2 lines for our power supply. We'll talk more about that later. We'll indicate a light bulb in that circuit there. If we want to measure the current, we don't measure it across somewhere in the circuit. We basically hook up the ammeter to somewhere in the circuit like that, and that will tell us how much current is flowing through the circuit. So we just measure in the circuit. So if we were using leads here, if we had a lead that went from the power supply, oops, don't mean to do that. If we had a lead that went from the power supply here to the light bulb, we would just plug that lead into one side of the ammeter, and then from the other side of the ammeter we would go to the light bulb. So the ammeter is part of the loop in the circuit, and that'll tell us how much current is flowing through the circuit. Again, we're going to come back and look at series and parallel circuits later, and we'll also look in the lab about how we measure voltage and current and make some simple circuits. Also, we want to just talk about a couple of safety devices that you'll often see in circuits, and they particularly relate to electrical current. So the first is fuses. You might find fuses like this in your car. Older houses often still have fuses like this. And we're only doing this at a fairly simple sense this year. Fuses are designed to melt if a fault causes too much current to flow, breaking circuit to switch off flow of electrical current. So sorry, that's not really clear. But basically what's going to happen is if too much current flows through this fuse here, this little bit of wire here will melt. As soon as that melts, that stops the flow of electricity, so it turns the circuit off. And usually that too much current will only flow if there's a fault or something goes wrong in the circuit. So it's a way of protecting the circuit from having too much current flowing through it for too long, which could lead to a fire or do greater damage or something like that. So again, later on we'll look at fuses in the lab, and we'll demonstrate how a fuse works and blow a few fuses. The other safety device that's more regularly used now in houses is these things called residual current devices, or RCDs, or you might also call them circuit breakers. And what they do is they constantly monitor the current flowing into a circuit, and they monitor the current flowing out. So they monitor, if you like, the wire, if you've got this circuit that's going to a light bulb, they monitor the current going to the light bulb and the current coming back from the light bulb. If any of that current is lost, so if that current there is not the same as that current there, i.e. there's some residual current, it's what goes in isn't equal to what comes out, that's where the residual comes from, then it will immediately cut off the power. And the reason it does that, because if you're losing power, it's probably because it's going through a person rather than the circuit. So if, okay, let's say this was, instead of a light bulb, was a toaster, and if I stick my knife in the toaster and the current, rather than going in one wire and out the other wire, suddenly goes and tries to travel through me, which is basically what happens when you get electrocuted, the current flows through you rather than keeping to flow through the circuit, it will realise, oh, there's being some current lost here, and it will very, very quickly flick that circuit off, hopefully before I get too much damage done to myself or anyone else silly enough to stick a knife in a toaster. So that's a very basic introduction to how fuses and RCDs work. But I think that sort of ties in well with that idea of current flowing through a circuit, and how we can use the measurement of that in an RCD, or how we can have a system that basically causes the current to shut off if the too much current flows. When we talk about the heat topic later on, we'll talk a little bit about why these wires get hot, and why if too much current flows they will get too hot and break, but I will save that detail for later on. So that is electrical current and also voltage, and that's it for this episode. Thanks for listening, or thanks for watching.